Okay, so picking up where we left off, we talked about the idea that when we have either a point force or a couple, an applied couple, or a distributed load, there's some general trends we see about the shear and bending moment along the beam. We know that for a point force, the shear is going to jump discontinuously by the amount of the applied force, but that the bending moment will just change slope at that point. Similarly, for the applied moment, we know that the shear force diagram will not be affected by an applied moment, but that the bending moment will jump by minus m, according to our sign conventions, as we pass the point of the applied couple. What we want to establish is more general relationship for a distributed loading. So when we have a distributed loading, we have some sort of intensity function, which we designate by w of x as this function of x along the beam. And what we'd like to figure out is how does the shear diagram and the bending moment diagram relate to the shape of the intensity of the distributed loading function. And so one way we can analyze that is to imagine some small slice of the beam that has a width delta x as indicated, which is at some location x as measured from the left end of the beam. And if we magnify that little location and look at that portion of the beam, we recognize that on the left side, if we're following our normal sign conventions, we have a shear force V pointed upward and a bending moment pointed clockwise. And on the right side of that little slice, we have a shear force V plus delta V pointed downward, where note that here the shear force is not the same as on the left side, but is some small amount different from that. And similarly, we have a bending moment on the right side that is counterclockwise, represented as m plus delta m, where we acknowledge that the bending moment is different from that on the left by some small amount delta m. And in terms of the distributed loading, we've taken whatever the distributed loading function is and represented that distributed loading by its equivalent force, and we know that the equivalent force is just equal to the area of the distributed loading curve. Now, if that is a small slice, that would be equal to whatever w of x is, which we can assume is approximately constant there, times the width of that section, which is delta x. So that gives us the area, and that therefore is equivalent to our small force delta F for that equivalent loading. And as far as the location, it's not necessarily right in the center. That will depend on the shape of the distributed loading curve. So we could acknowledge that maybe at some distance k delta x, where k is a fraction. If it were a rectangular loading, k would be 1/2. The middle, but it could be smaller or larger than that depending on the shape of that function. So now all we need to do is write our usual equations for this small segment of the beam. That is, we can write that the sum of the forces in the y direction is equal to 0. And if we do so, we have V pointed upward on the left plus delta F, which we see is w of x times delta x. And then we have a downward force, so minus, and the amount of that downward force is V plus delta V. So now if we distribute the negative sign, we see we're going to have a V minus V, so those will cancel out, and we'll be left with a minus delta V in this term w of x delta x, or in other words, we can move the delta V to the other side, and we'll have delta V equals w of x delta x, or if we divide both sides by delta x, we'll have delta V over delta x is equal to w of x. And finally, we can take the limit as delta x goes to 0 as we shrink the size of our slice in the bean, smaller and smaller, to a differential. We just simply then get the definition of a derivative on the left. So we have dv dx is equal to w of x. Or in other words, the slope of the shear force diagram will be equal to the intensity function at any point. So as the intensity function changes, the slope of the shear force diagram will change. If we integrate this function, both sides, from some point x1 to some point x2, then we simply get that V2, that is the shear force at some location x2, will be equal to the shear force at some location x1 plus the integral from x1 to x2 of w of x dx. And of course, this integral just represents the area of the shear force diagram. So another way of saying that is if we know what the value of the shear force is at some location x1, we can just integrate the loading distribution function and find the area between x1 and x2 and add that on, and it will give us the shear force at the next location at the other end of that segment of the beam. Similarly, we can take the same sort of approach to look at the bending moment by taking some of the moments about what is marked as point O in the diagram, where the dot is. And so we have some of the moments about point O, which will have a minus m, since that's clockwise, plus m plus delta m, and then we'll have the moment that V causes about O, which note will be minus V times its perpendicular distance, delta x, and then we'll have the moment that delta F causes about O, which again will be minus, and that will be W of x delta x, times its perpendicular distance, which is k delta x, and then finally V plus delta V doesn't cause any moment about O since it passes through that point. So this is the sum of all the terms that cause moments about point O in our diagram below. So note that minus m and m cancel out, and we can then solve for delta m. And we'll go ahead and divide through everywhere by delta x. So we'll have delta m over delta x. And then we've moved the other two terms to the other side of the equation, so they both become positive. And we divide the v delta x term by delta x, we'll just get v. And then we have this other term, w of x. And then we've divided by delta x, so one of those drops out, but we still have times k delta x. And finally, we want to take the limit as delta x goes to 0. And so the left-hand side, again, is the definition of a derivative, so that just says dm dx is equal to, and then the right-hand side, as delta x goes to 0, the second term becomes infinitesimally small. In other words, that goes to 0, and so we're just left with v. Or in other words, our conclusion is similar to that above, that the slope of the bending moment diagram at any point is just equal to the shear force at that same point. And just like above, if we wanted to integrate, we would find that m2 is equal to m1 plus the integral from x1 to x2 of v dx. So in other words, if we integrate the shear force from point x1 to point x2 and then add that on to whatever the bending moment is at point x1, that will tell us what the bending moment will be at point x2. And again, note that that integral just represents the area under the shear force curve. And so this can give us a shortcut approach anytime we have some sort of distributed loading for figuring out what will be the shear force for any region of the beam based on the loading diagram, and then what will be the bending moment along the beam based on our shear force diagram. So let's take that and apply it to an example. So for example here, imagine that we have this cantilever beam. It's attached at point B, and we have a point loading of 2 kilonewtons at A, and we have a distributed load that's distributed over a distance of 2 meters and has a constant downward force of 1.5 kilonewtons per meter. Now, we see, first of all, based on what we learned previously, that over at point A, we're going to start out on the end of the beam with no shear force, but then it's going to jump downward by 2 kilonewtons. And so essentially we're going to go from 0 to -2 right at the beginning when we hit this point load. Then in the central portion of the beam, we have W is equal to 0, and we know from what we just derived that whatever W is equal to is equivalent to the slope, or in other words, dv dx, in that same location. So if W is equal to 0, then dv dx is equal to 0 in that same region. And of course, if dv dx is 0, that means that V is a constant. So V stays constant from 0 to 2. So we can say from 0 less than x less than 2, V is constant at a value of -2 kilonewtons, which is what we got from that point force. And then when we look for 2 less than x less than 4 in that region, W is equal to a constant -1.5 kilonewtons per meter, minus because it's pointed downward, and that tells us that the slope must also be equal to -1.5 kilonewtons per meter in that same region. Or in other words, V is dropping at 1.5 kilonewtons per meter. So V drops linearly at -1.5 kilonewtons per meter. And of course, if we wanted to know what V is at the end of that, we could just use our area approach. So V2, well in this case V at x2, which really is 4 meters, would be equal to V at 2 meters plus the area of W. And we know that V at 2 meters is this constant -2 kilonewtons, so -2 kilonewtons, plus the area of the distributed loading diagram, which has a width of 2 meters and a height of -1.5 kilonewtons per meter. And 2 times -1.5 is -3 kilonewtons, and so if we add that on to -2, it tells us that V at 4 meters is equal to minus 5 kilonewtons. Or if we want to look at that graphically, it looks like this. So here we see that, as expected, V starts out jumping down to -2, remaining constant until we hit 2 meters, and then dropping linearly down to a final value of minus 5 kilonewtons. Now, qualitatively speaking, we know that from 0 less than x less than 2, we can see that V here is constant, and it's negative, which tells us that m, the slope of m, dm dx, is also constant and negative. So in other words, m must be dropping in that region. So m drops linearly. And from a quantitative perspective, we can see that the value of V, its constant negative value is -2, which means that the slope of m must also be -2 kilonewtons. So m drops linearly at -2 kilonewtons. And then we can see, once we go over from x equals 2 to x equals 4, that V drops linearly, or in other words, V is negative and decreasing in value, which means that dm dx must also be negative and decreasing in value. In other words, the slope must be negative and decreasingly negative. Moreover, since V is linear in this region, or in other words, first order, if we integrate that, we know m is going to be second order. So it's parabolic, and it has a negative and decreasingly negative slope. And in fact, we can also figure out from the areas, if we look at the shear force diagram, we see that the area of this first section is just -2 times 2, or -4 kilonewton meters. And in the second section, it's a width of 2, and this is a trapezoid, so it's the average of the two heights, which would be -2 and -5. So the average of those would be -3.5 times a width of 2 gives us a total of -7 for the area of that region. And so we know that the bending moment is going to go from 0, it's going to drop to -4 linearly with a constant negative slope. And then, after x equals 2, it's going to drop by another 7 kilonewtons per meter from -4 to -11, and it's going to do so in a parabolic fashion. Or in other words, it'll look like this. Right? So m goes from 0 to -4 in a linear fashion, and then from -4 to -11 by a second order parabolic function. Okay, so let's take one last example, and this time let's look at things in reverse. So let's imagine that we know the bending moment diagram, and we want to try to deduce the shear force diagram and the loading. So here we see first off that m is cubic, or in other words, third order. And so qualitatively speaking, we know that if M is third order, then V must be one order less than that. So V must be second order. And if V is second order, the loading diagram W must be one order less than that, so it must be linear, first order. So we'll expect to see a first order or linear distributed loading diagram, and now we just have to work out the quantitative aspects of that. First, I'll point out, we know that if this is a cubic equation for M as a function of X, that means that M must be equal to A0 plus A1X plus A2X squared plus A3X cubed. Right? There's a general cubic equation where we need to determine what are the constants A0, A1, A2, and A3 for that cubic equation. And I won't go through the details here, but I'll leave it as an exercise for you to show that if we know the following, M at x equals 0 is equal to 0, we can see on the graph at this point. We also know that M at x equals 12 here is also equal to 0. And we know at M at x equals 6.93 is equal to 1109. And finally, that dm dx at x equals 6.93, the peak of this function, that derivative is equal to 0 because it's the maximum. That gives us 4 equations, essentially, by plugging in each of these above and solving that system of equations. We can solve for the values of A0, A1, A2, and A3. And if we do so, we would get this equation that M turns out to be equal to 240x minus 5/3 x cubed. In other words, A0 is 0 and A2 is 0. And so we actually just have a first order term and a third order term for this particular function. Now note that if M is equal to 240x minus 5/3 x cubed, we know that V is equal to the derivative of M with respect to x. So it must be equal to 240 minus 5x squared, which gives us the parabolic function. We knew that V was second order. This is the second order function for V. It's just the derivative of the function for M. We also note that everywhere we look at the slope for the M curve, we know what the value is of the V curve. So for example, right here, we see that the slope of the M with respect to x is 0, and so the value of V must be 0 at that point. And so we know that this parabolic function crosses the x-axis at the point 6.93. We also know that V is going to increase, the slope of M is positive in this region to the left of that point, but it's decreasingly positive as it approaches 0, and so we know that V will be a positive number to the left, but it will be approaching 0, will cross at this point, and then, because the slope of M is negative over here, and increasingly negative, V will similarly become negative and increasingly negative as you go to the right at that point. And so in other words, you get something that looks like this. And it's worth pointing out that we know that as we go from M equals 0 up to m equals 1109, that v, the area under this curve, must be equal to that change in m. Or in other words, the area of this region must be 1109. And similarly, to the right of that point, m goes from 1109 back to 0, or in other words, it drops by 1109. So this area must be negative 1109 if we were to integrate this equation from 6.93 to 12, we would get negative 1109. And those two areas balance each other out in this case. Okay, now finally, deducing what the loading diagram looks like, we can tell that if V has a slope that is negative and increasingly negative all along its length, then we know that W must be negative, have a negative value, that is, be downward, along the entire length from 0 to 12. And in fact, if we wanted to, we know that W is equal to dV dx, the derivative of the shear equation. And so if we just took the derivative equation below, we can see that W must be equal to minus 10x. Or in other words, it starts out with a value of 0 at x equals 0. And then as x goes to 12, it becomes minus 120, or in other words, a downward force of 120 pounds in this case. So it just looks like a triangular loading distribution. As shown here, that goes from 0 to minus 120. And also note that the shear force must be equal to whatever the reaction force was or applied load on the end of the beam, because it essentially jumped from nothing to a positive 240, and then it followed this negative linear slope along here. And then finally, over at the right end, the value of the shear is minus 480 in order to react to this 480 on the right end of the beam. And that over this region, it's dropped from 240 to minus 480, or it's dropped by a total of 720, which means that the area of this loading diagram must be equal to minus 720, which of course, pounds that is, which of course it is, because it's just equal to 1/2 of the base times height, which in this case is 12 times 120, and then half of that, so 6 times 120 is 720. So in fact, that is what we see. Okay, so again, that allows us to see how we can calculate shear and bending moment diagrams and to draw conclusions from looking at shear and bending moment diagrams. Again, the main idea is that you can slice a beam anywhere along its length using a variable x for the position, and use your basic approach of drawing the shear and bending moment at that cut portion and solving for the equation, and then also using these simplifying relationships that the value of the intensity diagram corresponds to the slope of the shear diagram, and the value of the shear diagram corresponds to the slope of the bending moment diagram. All right, and I recommend you tackle some of the homework problems and example problems in our review set, and we'll talk about this further on Tuesday.